So let's start. So there was some confusion in the end of the last class about how to go about finding out the inter-reciprocal network and how to go about thinking about it mostly, right? So we kind of stumbled upon on the right solution in the end, but later I realized that there is a better way of approaching it when you are approaching from a 0th level perspective, right? So the part that was missing in the argument is as follows. So let's do that voltage control voltage source itself, then probably it will become clearer. So we were trying to figure out a hatted network here. And what should this inter-reciprocal network look like? So we use telegons. So simply writing telegons becomes V1 times I1 hat plus V2 times I2 hat becomes equal to V1 hat times I1, which is 0, and V2 hat times I2. Now, the whole purpose of doing this reciprocity of inter-reciprocity is to interchange the excitation and the observation ports, right? So the thing that we would like to do is definitely to apply an excitation at port 2, right? So now the question that needs to be answered is that should I apply a voltage excitation or should I apply a current excitation? There are only two options. So if we apply a voltage excitation, for example, so what does it come up to? So I apply a voltage excitation. So I am not sure what I have to do in the port 1. So I've left it as is. So if we do this, what does this, which term goes to 0? So clearly in this case, or rather, I mean, so this definitely remains as is, V1 I1 hat plus V2 I2 hat, right? So V2 I have, V2 is here, right? So V2 is not 0 anyhow. V2 times I2 hat. So now this remains 0 plus V2 hat I am applying. So this definitely I do not want to make it 0 and times I2. So clearly this term I want to retain, right? And this term I want to make it to go to 0. If I apply a voltage excitation at port 2, correct? So now if I want, how do I make this term go to 0? I have to essentially make I2 hat to be equal to 0. Right? So which essentially means that this becomes an open circuit here. Right? So this goes to 0 if this is open circuit. So then I'm left with these two, right? So which means that V1 I1 hat is V2 hat times I2. Now, this is the term, this is my excitation in the inter-reciprocal network. What is the observation? Observation is I1 hat, correct? So basically, I1 hat becomes I2 by V1 times V2 hat, right? So if there is nothing wrong so far, there is no, I mean, we have not violated any principle, but is this useful to us? Is this format useful to us? That is the next question that needs to be answered. So for it to be useful to us, I need to know this explicitly, correct? But now what is I2 over V1? I2 over V1 over in the original network. Do I know I2 over V1 explicitly? We don't know, right? Because we don't know, this type of inter-reciprocal network will not be useful to us, right? So I ultimately want it in the format so that the stuff inside this hatted network is known to us explicitly, correct? But if I apply a voltage source here, then what we'll end up with is a format this probably would look like this. This looks like a voltage control current source, right? This format looks like a voltage control current source. This is applied in voltage. This is observed current. So if I have to draw a circuit, then this should look like this. V2 hat. I sense this and push a current. This is I1 hat. So I1 hat direction will be this is positive. And this will be some G times V2 hat, where G is I2 over V1 in the original network. But this is unknown. If this is unknown, then this type of network is not useful to us, right? But if I then decide not to apply excitation of voltage, but excitation of current, right? Then we retain this term and get this to 0. Right? That's what we did in the last class. Right? So if that is the case, then the ratio I am ending up with is V1 over V2 or V2 over V1. That is known to us. Because V2 over V1 in the original network is the voltage gain of the voltage control voltage source. Right? So the reason I spent this 2 minutes on this is for you to appreciate the fact that it is not only sufficient to establish a port relationship, right? Elegance will hold regardless. But whether it will be useful to us, that usefulness comes from the fact that I should be able to represent that inter-reciprocal network in such a way that there is a fixed relationship between the ports. Correct? For that to happen, I have to make a intelligent choice as to should I excite the port 2 with a voltage source or a current source. Correct? So that's the another level of decision making, which was implicit, but I did not explicitly mention in the previous lecture. Okay. Okay, fine. So in the inter-reciprocity, so till now, what have we done? We have basically said that in the original network and in the inter-reciprocal network. So in the original network, if I have a voltage controlled current source, this gets, this is 1 dash, 2 dash. This gets replaced with what? VCCS gets replaced with VCCS only, but with the flipped terminals, right? So this remains as is. So this is GMV1 1 dash. This becomes GMV2 2 dash. Right? Similarly, if we have a voltage control voltage source, this we saw in the previous lecture. This gets converted into current control current source, right? So this becomes current controlled, as in you have a short circuit, because current control sources have input impedance of 0. This is 1 time. So this is A times, if this input current is I2 hat, this is A times I2 hat. And what will be the direction of current? Going up or going down in the control source? Going up, right? So the easy way to remember, here if this increases, this port voltage increases. So if this current increases, this current should also increase, right? So that's the in the direction of given to us, right? Okay, fine. So there are 2 more. So this is VCCS. This is VCVS. There are 2 more. Let me do 1 more, and then I will leave the other to you. So let's do the Let's do the current controlled voltage source, for example, right? So let's do CCVS. So let's say this is a current control source, that is if I have I1, this is a voltage source. So this is R some, let me just call it R times V1. This is R is basically, it's not a resistance, but some variable whose the coefficient whose unit is a resistance, because I'm converting from I to V, right? So I need to form a reciprocal network or inter-reciprocal network, which will give me the same transfer function, right? So that's the whole idea. This is at. Oh, sorry. Yeah, thank you. R times I1. Okay, so now let's write out elegance. So V1 is clearly 0, right? So the first term goes to 0. Then V2 times I2 hat should be equal to V1 hat times I1 plus V2 hat times I2. So again, by the same principle, we would like to excite port 2. Should I excite port 2 with a current input or a voltage input? That's the decision we need to make. What do you think should we do? Okay, current input. Let's see current input. So let's say I excite port 2 with a current input. So this becomes I2 hat. So when I'm saying current input, I'm basically saying I'm retaining this term. Correct? And what about which V2? So this term anyway. Okay. So what about this term now? So do I know, by the way, do I know I1 explicitly? I1 I know explicitly, right? Because it's a current control source. Input is current. So I know the I1. So there is no ambiguity here. Do I know I2 explicitly? No, right? So which means that's a problematic term. So I2 I do not know. So I will set V2 hat to 0 so that I don't have to deal with that term. Correct? So let's set this to 0, right? So set this to 0, which means V2 hat is 0. Right? So this is if V2 hat is equal to 0. So which means this is shorted. Correct? So pardon? Okay. So so here I have to do something. So what did I end up with? If that becomes 0, I ended up with V2 I2 hat is V1 hat I1. What do I need? I need the V1 hat, right? So essentially V1 hat becomes V2 over I1 times I2 hat. So this is again a current control voltage source, right? Where I have something here whose value is V2 over I1 times I2 hat, right? Or V2 over I1 is what? R. So this will be R times I2 hat, and this is V1 hat, right? So what about the direction? It will be plus on the top or plus on the bottom? Will it be this or the other way around? Look at this, right? So what is it telling you? If I2 hat increases, V1 hat should increase. So is this correct or do we have to flip? Correct, right? Okay, fine. So basically then we have the third one. So if we have CCVS, we will, so we have CCVS. So this gets converted to again CCVS, but now flipped in direction. Okay, fine. So I'll not do the other one, CCCS. I'm pretty sure you can guess what it will be. What will it be? CCCS will be? Yeah, it will be CVS, right? You don't even have to do it because here you basically go from there to there. Right? So either way, it's fine. So I'm sure you are doing this in many of these configurations in analog circuit course 610, or you have done it in UG level in 210 and so. So what is a VCCS in a transistor level? It's basically a transistor. It's a voltage control current source. A MOSFET is a VCCS. If I neglect all the other second order terms. Example of a VCVS? Common drain, but I mean, even if you do not get into transistor level, I know an op amps, for example, right? An op amp is a voltage control voltage source, zero output resistance, infinite ideal op amp, right? What about current control voltage source, CCVS? No, right? Resistor will not have a zero input impedance, right? Huh? No, it's not transconductance. It's current control. Transconductance is voltage control current source. This is current control voltage source. Right. So something with a resistive feedback, for example. Have you seen this circuit, this type of thing? If I make an op amp, it will become clear. So let's say I use an ideal op amp. And say this. Can you comment what is the input impedance here? And if A is infinite, 0, right? So this is a current control source. By the way, how do you know it's a current control source or a voltage control source under ideal situations? You look at the impedance, right? If the input impedance is infinite, it's probably a voltage control source. If the input impedance is 0, it's a current control source in idealized situation. So this input side is current control, that is satisfied. Output side is, what is the output impedance? 0, again, ideal op amp, right? Even negative feedback and all those things. So if you assume A to be infinite, the output impedance will be 0. So input impedance 0, output impedance 0. So it's current control voltage source. And you kind of, this is one example. What about a current controls current source? Yeah, it's a current buffer. Using a single transistor, can you make a current buffer? MOSFETs, using MOSFETs. Yeah, right. So you can say not common, it's common gate, right? So yeah, so if you have this configuration, or I mean, if I draw it like this, assume transistor is in saturation and infinite R naught and all those things. Incrementally, the output impedance is infinite. From here, this is like, if GM is infinite, this is 0, right? Tends to, I should write, tends to. So this is kind of a current buffer. Okay. So you see, all of them have some real life usage, right? So so the reason this becomes useful is because when you what a simulator does, your circuit analysis or small signal analysis and all, if you have multiple of these sources and multiple of these control sources here and there, and like the problem that you did at the beginning of in the quiz, right? So you had 2 current sources and you are taking output from one. So one possibility is to use superposition, but in that case you have to find out n number of solutions. Alternate is using reciprocity or inter-reciprocity. In this case, you apply input one at one position and just read out the voltage or the currents across different positions, and that will, and then you combine them mathematically, and that gives you the output, right? So hence inter-reciprocity becomes very, very extremely crucial for making circuit simulators also, right? Not only to make our life easier, but these algorithms are used while in CAD design also. Okay, fine. So let's do one example of this voltage control voltage source, the op-amp, ideal op-amp scenario, right? So uh, just to convince ourselves that this works. So let's do one example of a voltage controlled voltage source in a circuit. For example, we know we're familiar with this topology, right? Let's say I call this V1, V2, and let's say this is ideal op-amp. If this is an ideal op-amp of gain A tends to infinity, then I know that V2 over V1 is minus R2 over R1. So we would like to do this using the inter-reciprocity as well, right? So in order to do that, what should I do? First thing, let's write this, let's express this op-amp in terms of voltage control voltage source, which an op-amp, ideal op-amp actually is. So this becomes this should be plus V2 R2, and the gain here should be A or minus A. This should be minus A because I have flipped terminals here, right? Here I have minus is plus. So basically from, if I call this VE, from VE to V2, I have a flipped gain, right? So if I call this VE, it is in order to ensure that the figure on the top and the bottom are identical, then this should be negative positive gain of A, where A tends to infinity, right? Okay. So now I want to do this with respect to, I want to do the same analysis using inter-reciprocity. So what should I do? The easiest thing to do is to put down the things that won't change. Firstly, what are the port definitions? So this is the port definition, right? So this R1 remains R1. This R2 remains R2. Okay. Now this voltage control voltage source becomes current control current source, right? So before doing that, what should we do? We should basically apply an excitation. An excitation in this case will be, because I am applying a voltage source here and I'm getting a voltage output, right? So I'm getting V2 over V1. This corresponds to what? This corresponds to I2 hat. You excite port 2 with I2 hat, and you observe the current in port 1. This is I1 hat. And what is the relationship when you do reciprocity? In general, if you apply V1 and you observe V2, right? The reciprocal behavior is you apply I and observe I1, but it should be I1 hat or negative I1 hat. If you recall, it should be negative I1 hat, right? So again, so basically what I'm saying, this is corresponding to I2 hat by negative I2 hat, or rather negative I1 hat times I2 hat, correct? Okay. So in other words, this is what that should happen, right? Why should, I mean, how to remember this? Why should this happen? because ultimately we are bothered about the terminal characteristics. If this were true, then we get V1 I1 hat plus V2 I2 hat is 0, right? Which is the correct expression, correct? So it should be negative I1 hat, which essentially means that here I have to change up the direction of I1 hat, and this would be the direction I1 hat going in the yeah, in the arrow pointing downwards, right? So that is an adjustment that you have to make when you are doing when you are replacing the when you are applying V1 and observing V2, and the reciprocal network, you are observing you are applying I2 bar and you are observing I1 hat. Okay. So that is number one. And number two is you have to now we go inside the network and we see that we have this voltage control voltage source. Now that also needs to be replaced. Now what should we replace it by? This is easy. We should replace it by current controls current source. So the controlling terminal is here. This, let's say I call this IA, and this will be the current control source of value A times IA, but going up or going down, this will be going up, right? Because this is simpler to remember, because if this goes up, this should go. Okay, so if this goes up, for example, if I have a voltage control voltage source, it points like this, then if this goes up, this goes up. So similarly, if I replace it with a current source, the current comes in. So at the output side, the current should also go out so that the corresponding voltage equivalent goes up, right? But in this case, in our case, this is flipped, right? So we should also flip this. In this case, this becomes this. Or in other words, if we have to be strict, we have to basically say that this is going upwards and this is negative IA, right? So let's stick to that since we are doing it for the first time. Now in the second step, I can say this goes down. This is AIA. I2 hat, IA, R1, R2. I'm interested in this I1 hat, right? Okay. So I know that in this case, I1 hat by I2 hat will be is equal to V2 by V1, right? In this case, V2 by V1. So let me just remove this up just to ensure the confusion does not arise. Okay, so all I have to do is now find out the relationship between I1 hat and I2 hat. Fine. So let's do that. So note that this is a common ground. If this is I1 hat, then I know that this voltage here is how much? This is I1 hat times R1, right? Okay. This current, so this current is I1 hat. The current going down is AI bar. So this current is AIA plus I1 hat, right? So this voltage becomes how much? So by the way, this voltage is essentially 0 because that is also connected to, that is also shorted. So the current, if I do a KCL at this node, what do I get? The KCL at this node is I2 hat is the current going in is equal to IA plus the current that is going out, which is AIA plus I1 hat, which essentially means that if I divide everything by A, I get I2 hat by A equal to IA by A plus IA plus I1 hat by A. So if A tends to infinity, right? So if A tends to infinity, then clearly IA goes to 0, right? Note that IA goes to 0 does not mean AIA goes to 0, right? Because A tends to infinity, IA tends to 0 can lead to a finite solution. So we will not set AIA to be 0, but we definitely know for sure that this is equal to 0, which essentially means that now if I again go back and do find out the voltage at this point, right? What would be the voltage at this point? That will be the voltage at this point minus the drop across R2, right? So voltage at that point is I1 hat R1. And since the current direction is flowing into that node, so this point, which is 0, right? 0, this is equal to, so 0 is equal to I1 R1 plus AIA the better way to look about it is this. Now, if IA is 0, I know that this current completely flows through this path. Okay. And I know for sure that this voltage is 0. And this voltage is I1 R1. So which essentially means that I1 R1 hat is equal to 0 minus I2 hat times R2, right? Which means that I1 hat by I2 hat is equal to minus R2 by R2. Correct? So this is what we are anyway supposed to get if we were doing the brute force analysis using an ideal op amp, right? So just like in an ideal op amp, you were seeing this VE to be equal to 0, right? V goes to 0, which means you have a virtual short. In a voltage controlled, in a current controlled current source, we have a virtual open. That is, even though you have physically shorted the input ports, the current through the input port is essentially 0. This is equivalent to that virtual short in case of a voltage control voltage source. We have a virtual open in case of a current controlled current source, right? So this is something that we need to keep in mind. So the next thing that any analog circuit designer should be aware of, especially when you are designing circuits to handle weak signals, is the effect of noise. I think I briefly touched upon this in the beginning of the course in a very qualitative manner, that even if you have let's say you are capable of designing amplifiers of like 1000 dB, million dB, and so on, right? Even though it's virtually impossible to do that, but let's assume you are able to do that. Even then, it is in a practical scenario that will be useless because there is essentially noise associated with every device, right? So because there is noise associated with every device, when you are making an amplifier, in some sense, you are also amplifying its own noise, right? So it's not sufficient just to say that just because I have an amplifier, I'll be able to amplify any signal. Yes, probably you will be, but you'll also be amplifying if you have also the stuff that you are using to amplify is also noisy, then you will be amplifying its own noise also. So the design, as a designer, it is not sufficient to say that I am only designing amplifiers having very large gain. I'll have to also be I'll also be able to understand what is the noise impact of the amplifier. Okay, so that is the next part of our discussion. So we would like to develop a framework to analyze noise, right, and then use it for our circuit analysis. So so if you go to the lab, for example, and you take a resistor and observe its voltage in a voltmeter or in an oscilloscope, and under the assumption that the oscilloscope is extremely accurate, the accuratest oscilloscope that you can get, right? What would you observe? Ideally, what would you see? This is a floating resistor. You put a voltmeter, not a voltage source, a voltmeter. You put a voltmeter. What will you observe? Zero, right? Ideally, I should be observing zero, right? But as it turns out, you never observe zero. You will always observe some fluctuations. So the reason behind this, the intuitive reason behind this fluctuation is essentially your resistors are made up of, if it's a semiconductor resistor, for example, it is made up of certain crystal structure, and at finite temperature, there is always electrons and holes which are randomly moving around, right? So even though it's an equilibrium in a macro sense. It's not an equilibrium at the micro sense, which means that if you, it's like a Brownian movement almost. You zoom in, you will always see the electron clouds. They are not static, they are moving all around the place. But on an average, across any cross section, the number of electrons moving across a cross section is always zero on an average, not instantaneous, right? So you take any block of resistor. So let's say this is a slab. This is just a slab, maybe a metal, maybe a semiconductor, I don't care. But you observe a cross section. And you sit here, and let's say you have this electron microscope, you can observe the electrons moving in any random direction. So on an average, you will see that number of electrons crossing from left to right will be the same as that is crossing right to left, provided you do not have if we have not put any excitation across the terminals. These terminals are open, right? Obviously, if you put some voltage, net current will flow, then you are going to see an average one direction movement. But under this condition that there is no excitation, then on an average, you would see that number of electrons moving towards one terminal will be different from the number of electrons moving towards the other in an instantaneous sense. On an average, it will still be zero, and has to be because current is zero. So now what we are doing in this hypothetical experiment, we are saying that we are putting a voltmeter. Or even if you are not comfortable with voltmeter in this analogy, let's say I put an ammeter, which is in principle a short circuit, right? So ideally it's a short circuit, which means the electrons that instantaneously which was going in that direction has a path to go, right? And which means that if it's like an ammeter having infinite precision, I will see a motion of that arm, right? That is detecting current or electron flow through the galvanometer, even though I have nothing connected across it. So which essentially means that if I do this experiment over a period of time, and I observe the current through this ammeter in certain direction, let's say I say this is the current direction. So I'm not going, ideally I should be experiencing zero, but I'll not see zero. I will see some fluctuation. Something, I don't know what. Okay, so this is thermally generated, and this is this we call it as thermal noise. Thermal noise current in this case. Okay. So all resistors contribute to thermal noise. In principle, any device that dissipates power contributes to noise, thermal noise. Okay. A capacitor does not dissipate power. A capacitor does not contribute to any thermal noise. Inductor doesn't dissipate power, and inductor does not contribute to any thermal noise. Okay. So resistors, similarly transistors, resistors, transistors, diodes, and everybody contributes to thermal noise, but these inductors, capacitors don't. Okay, so we'll not get into the formulation of how these noise equations came. What we'll do is we'll assume that people have figured out what are the equations corresponding. I mean, what are um, uh, the statistics of these noise, and then we will go ahead with our analysis, right? Now, to appreciate what I just said, you have to understand the fact that, let's say I do the same experiment. I put a galvanometer or ammeter here, and I'm trying to figure out this. I do this experiment now. I come today, I do that experiment again tomorrow, right? So what will I observe? I'll again observe some random stuff, right? But will this be necessarily be the same with respect to what I observed today? No, right? Because this is thermally generated random motion. You do not know what's going to happen. So you do this experiment like n number of times, you are never going, I mean, if provided you do it for sufficiently long amount of time, right? So you are never going to see any matching between the sequence that you are seeing on the top or anywhere else. But the thing that will be same across all of them, provided for each experiment you have observed it for like almost infinite amount of time, two things are going to be same. One is the mean of this current, right? So what do you think the mean of IR will be? The average of IR. It has to be 0, right? Otherwise, you are essentially getting power out of nothing, right? Mean has to be 0, right? So mu IR has to be 0. Similarly, I do this experiment any number of times, I'm going to get mu IR equal to 0, provided you have observed it for long enough time, right? If you observe it for, let's say, 1 nanosecond, then obviously you are going to get something. Right? So you observe it for long enough time, you are going to get mu to be 0. There is another thing, as it turns out, which is also constant. Now, this is not obvious, but I'll just state it. The another thing that is constant is its standard deviation is also constant. Okay, so in this particular cases, your variance, your sigma square is constant. So you do this experiment n number of times, you find out the variance. Variance is basically what you, by the way, how do you calculate variance? Right, so summation of sigma minus mu, mu is 0 in this case, sorry, summation of IR minus average of IR, which is 0 squared, right? If this is discrete, so if you do this discrete point, if you do not do continuous, if you do discrete, then you basically say that IR n whole squared over all n. If you are doing continuous, then you integrate and divide by time and all things, right? So if you do this, as it turns out that the in case of a resistor, or in case of any thermal noise for a particular device, this value will be constant. Okay. So far so good. This is just a fact of life I stated, right? I have not proved anything. I don't intend to prove this also, right? So that will take another 2 lectures. So this is kind of a fact of life. So if that is the case, how should I go about using this in our circuits? So now, first thing, what we don't know, we cannot predict what the exact noise current, or for that matter noise voltage will be. I just put an ammeter here. That's why I am observing a noise current. If I put a voltmeter, I would have observed a noise voltage, right? So both have the same genesis, random fluctuation. So I do not know. I cannot at all tell you that what will be the next observed voltage in the voltmeter, or the next observed current through the ammeter if I do these experiments. But what I can definitely tell you is the statistics is same. So naturally, it doesn't make sense for us to observe these things in time domain. I have to observe it in another domain where the statistics is a part of the math, right? Because in time domain, I cannot do anything. So hence, noise analysis is almost always done in a statistical domain. Okay, so you always talk about mean, variance, and you talk about in various domains so that you want to come to mean and variance. Okay, so that's the moot point of it. The another important point that I would like to emphasize is noise is different from interference. Noise clearly is unwanted, that we all agree. At least in this scenario, noise is, unless you are planning to generate random sequence, right? In that case, noise is good. So So if your noise is unwanted, so noise is not the only thing that is unwanted, right? So there can be any interference that also can come, which is unwanted. For example, uh, when you have power surges in lines, right? In your in transmission lines, right? So then some of the surges couple to your devices. That is unwanted, but that is not noise in this sense of the term, because that is predictable, right? So if you know when the power surge is going to happen, or a power surge that has happened at certain part, you know that I can mimic that power surge and do some processing on top of it, right? So that is interference, that is not noise. Okay, that is not random per se. I mean, if you say that I do not know when the power surge is going to happen, that itself is not known, then that is also random. But let's say that is not, that is known to us. Or for example, when you were doing a cell phone call, uh, you are receiving something. You are the signal that is coming from the receiver, from the tower. You are receiving it, and you are making a call. Your neighbor, your friend is also making a call to somebody else. But now the signal that your neighbor is sending and the signal that you are receiving are slightly at a different frequency. That is understandable. But your cell phone is also receiving, your antenna is also receiving that signal, which is not intended, right? But that's not noise, that's interference. Because you can stop it. If your neighbor goes away, then that will automatically reduce. There are actions that you can take. But this noise is, if you are using a resistor, you are always going to have noise. The only way to get rid of the noise is not use a resistor. Okay. So otherwise, if you use a resistor, you have to live with it. Okay, so that's the important distinction, that noise is not predictable. If you cannot predict it, we call it noise, right? Okay, in more particular, in this is called thermal noise, right? Because the generation is thermal. Okay, fine. So the next stuff that we now, this is one time domain experiment that we did, and I told you about some of these properties. So now, if we take the same resistor and do a volt in a frequency domain experiment, that is, I take this resistor. So instead of putting it in an oscilloscope, I put it in a spectrum analyzer. Now, what is a spectrum analyzer? So it's like a spectrum analyzer. A spectrum analyzer is nothing but it's a band pass filter with an extremely narrow pass band, whose output is the power that passes through that band pass filter. It's basically a power meter across a very small frequency range. Okay, so which essentially means that instead of putting a spectrum analyzer, I can say that I put a band pass filter of, let's say, 1 hertz bandwidth. Okay, and at the output, I check the power. Right now, power by definition is not instantaneous power in this case. It's an average power. Right, so you observe the wiggling for an elongated amount of time, you are going to see some fluctuations, right, at the output. And you take, if you are, so let's say I do this, I say that I observe only the voltage. I'm going to observe the voltage, and the voltage will have some fluctuation, correct? So this voltage will have some fluctuations. Something will be there. So I take in, when I'm saying power, what am I doing? I'm basically saying that if this is VT, I'm saying there is a fictitious resistor R across which this voltage has been applied, and I am doing this 1 over T, and T goes from 0 to infinity. Right? This is the definition of power, correct? Or if I just said this is T, limiting value of T tends to infinity, correct? This is power. So if I do this, so by the way, if I do this, this is similar to saying that I am getting a variance, right? By the way, I think I missed 1 over n here. So this is similar to a variance, correct? So this is variance. So essentially I am, but right now, if I set R to be equal to 1, then this is exactly variance, correct? So so basically, taking the output of the band pass filter and saying that I am observing a power across some fictitious R equal to 1 ohm is equivalent to saying that what is the variance of the noise that I was trying to estimate earlier. But note that I have made an important distinction with the previous experiment, and that I am not directly observing the voltage across the resistor. I am observing after a band pass filter. Okay, so I should actually say this. Let's say this is some center frequency f naught and bandwidth of 1 hertz. Okay, so I observe this, I do this experiment, I observe this, I get a value, right? So experiment 1, so I will plot. So this is, let's say, f. Here I am plotting this f, that is the center frequency, or let me call this f naught, center frequency of the band pass filter. P f naught. This is f. Okay, so I set the center frequency of the band pass filter to, let's say, 1 megahertz, and I observe the power. I get some value. Okay, I move it to 2 megahertz center frequency. I get another value, and I do this across all. And as it turns out, if you have an ideal, if you have a resistor, this will be a straight line. Okay, thank you. So this is variance. Right? So, and in principle, this is measured over 1 hertz, because band pass filter has a bandwidth of 1 hertz. Okay, so I will basically say this is powered per hertz. Okay, so as it turns out, this will always be a straight line. And if you can show it using theory also, you can do it with experiment also. I'll just tell you what will the experimental value will be. This will be equal to 4 times K times T times R. Okay, so obviously K is Boltzmann constant, T is absolute temperature. You don't have any control over that, definitely not over 4. R is the only thing that matters. And as this curve tells you that if R, if you have a certain value of R, it is going to give you a power per hertz, regardless of where you observe it in the frequency axis, and the value will be proportional to, or rather exactly equal to 4 kTR. Okay. Important thing to note is that it doesn't matter how you have made that R. You have used copper, silicon, Apple, doesn't matter. If it's a certain value, this will be your noise. It's independent of the material, right? So that itself is a fascinating thing. So the second part that is the important part of the definition. This power per hertz, there's a technical term to it. It's called power spectral density. And its symbol is S. And subscript V means I am talking about the power spectral density of a voltage. If I say subscript I, which means it's power spectral density of the current. But in both cases, note that this is not an actual power. It is basically variance, right? Because it has some volt square and I square. And if you assume that it is passed through a resistor of 1 ohm, you get the unit of power, and hence it's called power spectral density. The reason the nomenclature stuck because there is a relationship between this and if time permits later on, I'll try to prove that one. So as it turns out, there is a relationship between this and by the way, this is frequency domain representation, right? So there is a time domain representation of this, and that's called autocorrelation. So you can show that power spectral density, the way we have it's totally not intuitive with the way I have talked about till now. You can show that power spectral density is the Fourier transform of the autocorrelation. Okay, so you have done it in your communication courses, fine. If not, just take that from me. So because there is now, if you think of measuring the power of a signal in time domain versus frequency domain, what do you use? You use Parseval's theorem. Right, so you measure the power in time domain, you measure the power in frequency domain. There we are okay with saying it power, even though there is no resistance. right? We just say x squared and say it's power, right? So, so that nomenclature has stuck. So even though this is v squared, we still call it power. Is power spectral density. Okay, so at the back of your mind, you should keep in mind that this is volt square per hertz. This, if it's power, this is not watt per hertz. This is volt square per hertz or ampere square per hertz, right? So that's something that you should always keep in mind. Okay, fine. So this is as far as the statistics and how to characterize noise is concerned. So now the next question is, okay, out of time. So the next question is, so what? So we have this. So now I have to get an estimate. I will never going to use only one resistor as is. We are going to use this resistor in a network, right? So if given that there is a resistance which is noisy in a network, how can I model its effect finally? Okay, so because we are circuit designers, we understand everything in the form of voltages and the currents. So even though I told you that this is probably not necessary, it's not intuitive to talk about absolute, I mean, the current and the voltages in time domain, we'll still try to model everything in terms of currents and voltages, and then try to see with some transform, can I go to this domain? Okay, and that's what we'll do in the next class. But just to give you one intuition. So you saw that I had a resistor, and if I put a galvanometer or an ammeter and I short it, I'm going to get some current I, right? So I'm going to get some current IT, in fact, right? In terms of time also, I'm going to get a current. You can think of this to be a Norton equivalent. There is a short circuit current, right? So I can, which means that I can develop a Thevenin equivalent of this also. Correct. So this model does not really tell you where the current source is. So in order to incorporate that, I have to say that there is a noise current source IN, and this is a noiseless resistor R. Right. So here, so what I'm saying is, this is a noisy resistor. This I can model as a noiseless resistor R and a noisy current source. Right. And so in principle, if the modeling is correct, then if I short this, the current through this should be equal to the current through this. Correct? So similarly, if I have this formulation, it's not a stretch to imagine I should have this formulation also. I have a voltage equivalent and a series resistor R. Right? So basically Thevenin form of that. Okay. So in the next class, we will see how do I model this in terms of the power spectral densities, and then what impact it has in our overall analysis. And you are going to see how reciprocity, inter-reciprocity helps in these analysis. Okay. Okay, fine. We'll stop here. Thank you.